Hello everyone, today we present our work CATS, Combined Activation and Temporal Suppression for Efficient Network Inference. In the recent years, deep neural networks, DNNs, dominate AI applications like object detection, post-estimation, and semantic segmentation, but face the challenges of real-world deployment requirements on low power and low latency. Novel AI computing architecture, event-driven architectures are emerging to address this issue by exploiting the sparsity in DNNs. Such a sparsity-aware processor is inspired by the brain's operation principles to compute only the necessities in the network for energy and latency efficiency. As shown in the figure, for example, of a commercial event-driven processor GrAI-VIP, it demonstrates a roughly linear correlation between event density and latency for each tested deep neural networks. Here, an event represents a non-zero value in the activation maps or in the temporal delta maps. We will explain this in the following context. Therefore, the primary goal of this paper is to propose a method that induces more zeros in event maps, meaning activation maps or delta maps, so that the network achieves a proportional performance gain on the chip. In this work, first we develop a novel event suppression tuning method called CATS, which combines activation, suppression, and temporal suppression to minimize event coherence during the in both activation maps and temporal delta maps during network inference. Second, we observe that higher threshold value enables more event suppression in the temporal domain. So we propose an efficient differentiable temporal threshold search approach called DTTS, which automatically searches for the optimal power of two thresholds for each layer, enlarging the temporal sparsity while maintaining the model accuracy. Lastly, we also did a case study for on a commercial event-driven processor GrAI-VIP to show a real-world performance gain through our proposed method. In the middle block, we can see more details on our method. First, we apply the quantized sigma delta modulation on each convolution G in the network based on the distributive property of linear function. The delta xt is the subtraction of feature map x at time t and at time t minus 1, which induces larger amounts of zeros because of the massive redundancy in the continuous video frames. The sigma delta modulation on one convolution is visualized in the left figure in the block. We name the feature maps before subtraction as activation maps, and we name the feature maps after subtraction as temporal delta maps. Second, we find that combining activation and the temporal suppression results in accumulated suppression effect. So here L means the amount of event suppression between variance and baseline. The baseline is ReLU suppressed, if any. Larger L distance stands for the better suppression effect. Therefore, we integrate the sparsity penalties for both activation and the temporal in the total loss function. And we formulated the event suppression problem in training as the equation below. However, then we notice larger threshold values potentially potentially achieve more suppression, shown in the gray dots. However, each layer has different sensitivity of accuracy on the thresholding. Instead of manually assigning thresholds per layer, we propose to learn layer-wise power of 2 thresholds through backpropagation on task loss and sparsity loss and sparsity penalties. This is inspired by the neural architecture search. We put each power of 2 threshold in a single cell during training and learning the probability of each cell node through training. Then select the maximum one as a fixed threshold during inference. Remarkably, power of 2 is a very cheap operation on the hardware, but won't affect the sparsity gains in our method. In the experiment, we conduct a study of various AI applications, such as object detection, object checking, pose estimation, and semantic segmentation. Here, we only show the results of object detection and pose estimation because of the space limits. In the left figure of the bottom block, we see temporal suppression, which are the yellow curves. Consistently outperforms activation suppression, which are the blue curves, at different accuracy levels. This shows the effectiveness of our differentiable temporal threshold search approach in learning layer-wise thresholds and exploring temporal sparsity. Then we see the combined activation and temporal suppression, which are the red curves, considerably surpasses any single suppression approach at different accuracy levels, which confirms our assumption of accumulated suppression gains by penalizing the presence of events in both spatial and temporal domains. To identify the performance of our method CATS, we compare it with multiple state-of-the-art methods in either spatial or temporal domain. We studied the case of object detection by using a SSD on a hand detection dataset, which provides video data. We reproduce the SOTA methods in our implementation. The start after the method name indicates different suppression focuses. 1 star represents activation suppression, 2 stars represents temporal suppression. Note that CAT is the only one doing for both. As a result, CATS, the red curve, outperforms the others with a significant margin, and such suppression gap is enlarged when more tolerance is allowed on accuracy degradation. Finally, the charts under the hardware evaluation here demonstrate event suppression in CATS models alongside their performance advantage as FPS, latency, and energy over their stand trained counterparts, which named the base in the charts, and SOTA method star optimized counterparts. This shows that the event suppression gains from CATS can be effectively translated into performance gains on real-world hardware. Additionally, we also make a comparison between CATS boosted event-driven platform performance and widely adopted TensorRT enhanced GPU platform performance. Apparently, the comparison is not completely fair, since GrAI-VIP is approximately 57 times smaller and running with more than one order of magnitude lower power consumption than HGPUs. The results show CATS can boost the base model performance by a factor of 3. As we see, the blue is the base and green as the CATS. green is cat boosted. This clears parsing the capabilities of Jet's Nano in both latency and FPS. Thus, we believe cats can elevated event-driven processors as a superior alternative to GPUs for edge computing because of its low latency, high FPS, and low power consumption.